We're going to take a look at linear independence and what it means and how you can determine if a set of functions are linear independent. So let's start off with just two functions. I've got this blue case over here, and I've got 3x squared plus 6 and f2 of x equals x squared plus 2. And I want to determine if those are linearly independent. Well, let's apply this test. Here's the way we're going to define it. If I can take a constant times 3x squared plus 6 and add it to another constant times x squared plus 2. In other words, I've just got a constant times this first one plus a constant times the second. Now, if there's any value that I can find for C1 and C2 so that this is true, so that this expression is 0, then we say that those functions are dependent. So if there's any way I can find a C1 and C2 now, provided that they're both not 0. So one of them, at least in this case, one of them can't be 0. Okay, so let's see how this would go. For example, I would say this. I could say, well, I'm going to let C1 be 1, and I'll let C2 be negative 3. Now, if I do that, what I've done is I've found constants where if I put that in, I've got 3x squared plus 6 minus 3x squared minus 6. And yeah, that equals 0. So we say this. We say that those two functions, f1 and f2, are dependent because we were able to find the constants that made that true. Now, if you look over here at this pink one, we've got C1 e to the 2x plus C2 e to the negative 2x. Now, I can't find any constants, C1 or C2, that's going to make that equal to 0. So we say that these are linearly independent. Linearly independent. Yeah. So that's what we're that's what we're going to be trying to do, determine if a set of functions are dependent or independent. Now, let's look at another example real quick. Let's look at this one. And we've got f1 is x cubed plus 7. So let's start the process here. Let's say C1 x cubed plus 7. And C2 is x cubed plus 7x. Okay. And then we'll say C3, we've got x minus 1. C3 times x minus 1. And then C4, we've got just x to the 7th. Okay. Okay, C4, x to the 7th. Now I'm wondering, are there any choices that I can make for C1, C2, C3, and C4 that will make this equal to 0? Well, let's see here. What if I just have C1 equal to 1? Okay. And then what if I have C2 equal to negative 1? Okay. And then what about C3? Well, C3, maybe I could have that equal to 7. Okay. And then C4 is kind of a problem one because we've got x to the 7th. But I can just make C4 equal to 0. Because remember, that's allowed. You just can't let all the C's equal to 0. So if not all of them are equal to 0 and you get it equal to 0, then they are dependent. So let's see if this works out. If I put in a 1 for C1, I get x cubed plus 7. A negative 1 for C2, I get negative x cubed minus 7x. And then if I put in a 7 for C3, I get 7x minus 7. and then of course 0 for C4. And let's see what happens here. I got the 7's cancel, the 7x's cancel, and the x cubes cancel. Ooh, 0. So that set of functions we say it is a linearly dependent set because I was able to find those constants. Now, let's make a transition here. Let's suppose we've got a set of, or let's be more general. Let's suppose I've got a set of functions, f1, f2, all the way out to fn. We say that that set is linearly dependent on some interval if there exist constants, like we found up there, C1, C2, all the way out to Cn, and not all of which are 0, such that this is true. Okay? Then we say that that set of functions is linearly dependent. Okay? And that x, of course, the x that we're looking at all the x's in a given interval. Now, if the set of functions is not linearly dependent, it is said to be linearly independent. And what we're going to be concerned with here in a little bit is a linearly independent set of functions. That's what we want. Now, we're going to need a way to determine if a set of functions is linearly independent or not. And the way we're going to, what we're going to use is called the Wronskian. And it is, so we've got the Wronskian, here it is. And it's a determinant. So we take these functions. For example, we want to determine if this set of functions are dependent or not. So we take the functions and put them up here in the first row. The derivatives, we put them in the second row. And all the way down to the n minus first derivative. Okay. We put that down in the last row. And we find the determinant. And we say this, that the set of functions is linearly independent if and only if the Wronskian does not equal to 0. Because if the Wronskian equals 0, then we say, okay, this is a dependent set. It's independent if it doesn't equal 0. Okay, now let's move along here. Let's suppose that we have a differential equation, our homogeneous differential equation. This one right here, one like this. And let's suppose that our y1, y2, all the way out to yn, it's a set of solutions for that differential equation. Okay? And let's suppose that the Wronskian does not equal 0. That means that this set is linearly independent. And we say this. We say that that set is a fundamental set of solutions on whatever interval we're dealing with. It's a fundamental set of solutions. That's the way we talk about, that's the way we describe it. So this is a set of n solutions. They are independent. So we say that this is a fundamental set of solutions. Now, for a differential equation like this, that set of solutions exist. And we take that fundamental set of solutions and we make a general solution out of it. This is the general solution. Okay? We just take each solution, put a constant in front. So for y1, it's c1, y1, plus c2, y2, all the way out to c sub n, y sub n. And we say that's the general set of solutions. Now, you know, I said a fundamental set exists, and I said we could, here's what I want to make sure you understand. The importance of the set of solutions being independent. Because we need to be able to find these constants. We need to be able to find C1, C2, and so forth. So let's see if we can motivate why that's important. Let's suppose that we have a set of a differential equation here. Let's just do a second degree. And let's suppose the Wronskian is not 0. Okay? That means that there's a set of solutions, y1 and y2, that are independent. And I'm going to do this. I'm going to set some conditions. Now notice I've got my general solution here. This is my general solution. Okay. Now what I want to do is I want to say, okay, I've got the general solution. Let me set some initial conditions. Maybe say that, and look, I'm going to do this. Let me make this. Put an X in here. Let me put a T in here. I meant to put a T. Okay, so let me put this in. So let's just put some conditions here. Let's suppose that I have this initial condition. In fact, I'm saying, okay, y of t is equal to, let's say, k1. See? So I've got k1 right here. And let's say y prime of t is equal to k2. Okay, so I've got k2 right here. Now what I've got is a system of equations. And notice, let's suppose t is just some value in this interval that we're dealing with. Well, look what I've got here. I've got a system of equations, c1 y1 plus c2 y2. And then I've got another system, another equation, c1 y prime 1 and c2 y prime y2. Okay, that's a system of equations. The first one equals k1, which is a number. The second one equals k2, which is a number. Now look, if this is a system of equations, and if this system is independent, then I can solve this. I can solve a 2x2 system of equations. In this case, I would be solving for C1 and C2. And I can do that because they're independent. If they were dependent, I couldn't find a unique solution for C1 and C2. So look, understand the connection here with independence. When we're talking about an independent set of solutions, think about it this way. We can use that. If they're independent, we can get a system of equations, an independent system of equations, and find a C1 and C2. So you can see, you can kind of get an idea why we need an independent set of equations or solutions. Now let's see how this works. Let's just look and see how this would work. Let's suppose we've got a differential equation here. And I'm curious if this solution, y1 and y2, I'm curious if those are independent. So I'm gonna get the Wronskian. Okay, so here I go. E 2x, E negative 2x. Okay, so this is going to be a 2x2 system. Okay, and then down here is 2e to the 2x. Negative 2e to the negative 2x. Okay. Okay. Now let's see what this is. This right here is going to give me negative 2. Yeah, negative 2 when I multiply that minus 2 like that. Yeah. And that's going to give me negative 4, which is not 0. Therefore, this solution, y1, y2, that's a fundamental set. Okay. So we would say this, our general solution is going to be C1 e to the 2x plus C2 e to the negative 2x. There's our general solution. And we can find C1 and C2. Okay, now let's look at the green one. Let's look at a system of 3 solutions. So let's look at the Wronskian. Okay, so I've got e to the x, e to the 2x, e to the 3x. So here I go. I've got e to the x, e to the 2x, e to the 3x. Down here, the derivative. And then the second derivative. And let's see what we get now. I'm going to find the determinant. Now, remember how we find determinants. I'm going to use row 1 as my row that I expand the determinant about. So I've got this first, I've got this e to the x, and I multiply it. Now notice what I'm going to do is I'm going to find this determinant over here, okay? Because I take out this column and this row, and then I find the determinant of the rest of it. So how's that going to be? That's going to be 18 e to the 5th minus 12, that's 5x, not to the 5th, minus 12 e to the 5x. Okay, there it goes. See, I just multiplied these together minus these multiplied. Now, the next term, I'm going to put a negative in front because really this term, remember, is -1 to the row and column power. So this is -1 to the row plus column power. So this is like -1 to the 1 plus 2 power. That's -1 to the 3rd. So this is going to, that determines the sign. Okay, so anyway, I don't want to go back over the determinant. If there's, you can always come to me with questions. But so now here's what I've got. I've got e to the 2x. And then I'm going to find this derivative. So I've got 9 e to the 4x minus 3 e to the 4x. And then finally the last one, e to the 3x. And I'm going to take out this column, this row, and get this determinant. Okay, so here I go. I go 4e to the 3x. Whoops. 4e to the 3x minus 2e to the 2x. Yeah, there it goes. Okay, so let's see what I've got now here. I've got 6e to the 6x minus, let's see here, this is going to be 9 minus 3. That's going to be 6. Oh, this is an x here. I left off the x. Sorry about that. I'm bad about that. Okay, so this is 6e to the 6x. Yeah, there we go. And then finally, at the end, I've got 2e to the actually, I realize I've got another mistake here. This should be 3x, I believe. Let's see here. I've got, yeah, I messed up there. Sorry about that. Okay, so that's going to be 2e to the 3x, so that's 2e to the 6x. So there is 2e to the 6x. That's not equal to 0. So that tells me that I've got a fundamental set on my hands. Okay. Now, notice I made some mistakes here when I was working through this. I forgot to put the x's on here. I put that as a 2x instead of a 3x. So that's a good cautionary tale. So be careful when you're working through these determinants that it's easy to make a mistake. Now, so I've got a fundamental set on my hand, e to the x, e to the 2x, and e to the 3x. And now I've got my general solution. My general solution is going to go like this. It's going to be y equals c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. And there you have it. There's your general solution.